Have you ever looked up at the night sky and wondered what's out there? We see stars, planets, and galaxies. But what if I told you that everything we see, everything we know, makes up only about 5% of the entire universe? The other 95% is a cosmic mystery, and a huge chunk of that, about 27%, is something called dark matter. It's invisible, it's elusive, and it's one of the biggest puzzles in modern science. So, what exactly is dark matter? Well, the simple answer is, we don't know for sure. The dark part of its name doesn't mean it's black or shadowy. It just means it doesn't interact with light or any other form of electromagnetic radiation. It doesn't emit light, it doesn't absorb light, and it doesn't reflect light. That's why we can't see it with our telescopes, no matter how powerful they are. It's like trying to find a ghost in a pitch-black room. You know it might be there, but you have no way of seeing it directly. If we can't see it, how do we know it even exists? The story starts back in the 1930s with an astronomer named Fritz Zwicky. He was studying a huge group of galaxies called the Coma Cluster. He measured how fast the galaxies were moving, and he noticed something really strange. The galaxies were zipping around so quickly that the gravity from all the visible matter, all the stars and gas he could see, shouldn't have been strong enough to hold the cluster together. It should have flown apart millions of years ago. Zwicky proposed that there must be some kind of invisible mass, or Dunkelmaterie, as he called it in German, providing the extra gravitational pull needed to keep everything in check. At the time, his idea was mostly ignored. It was just too radical. But then, in the 1970s, another astronomer named Vi Rubin came along. She was studying individual spiral galaxies, like our own Milky Way. She was measuring the rotation speeds of stars at different distances from the galactic center. Now, according to our understanding of gravity, stars farther out from the center should move more slowly, just like the outer planets in our solar system orbit the sun more slowly than the inner ones. But that's not what she found. Instead, the stars on the outer edges of galaxies were moving just as fast as the ones closer in. This was a huge shock. The only way to explain this was if there was a massive, invisible halo of matter surrounding the entire galaxy, providing extra gravity. This was the same conclusion Zwicky had reached decades earlier, and this time the scientific community started to listen. Since then, the evidence for dark matter has just kept piling up. We see its effects everywhere we look in the cosmos. One of the most powerful pieces of evidence comes from something called gravitational lensing. According to Einstein's theory of general relativity, massive objects can bend the fabric of spacetime. This means that a large concentration of mass, like a galaxy cluster, can act like a giant magnifying glass, bending the light from objects behind it. When we look at distant galaxies through these cosmic lenses, the light is often distorted and magnified in a way that can only be explained if there is far more mass than we can see. By measuring how much the light is bent, we can actually map out the distribution of all the mass, both visible and invisible. And these maps consistently show vast clouds of dark matter surrounding galaxy clusters. It's like we're seeing the shadow of something we can't see directly. So, dark matter isn't just a quirky idea. It's a fundamental part of our universe. It acts as a cosmic scaffold. Think of it as an invisible web stretching across the universe. The visible matter, the stuff that makes up galaxies, stars, and planets, congregates along the densest filaments of this web. Computer simulations show that without dark matter, the universe would look very different. The large-scale structures we see today, the vast clusters and superclusters of galaxies, would never have had enough time to form. The gravity from ordinary matter alone just isn't strong enough. Dark matter provided the initial seeds of gravity that allowed gas and dust to clump together and eventually ignite into the first stars and galaxies. It's the unseen architect of the cosmos. This brings us to the billion-dollar question. What is dark matter made of? We know what it's not. It's not just dark clouds of normal matter, because we would be able to detect them in other ways. It's not antimatter, because we'd see powerful gamma rays when it annihilates with normal matter. And it's not black holes, at least not the kind that form from collapsing stars, because we would have detected their gravitational effects in other ways. The leading theory is that dark matter is made of some new type of subatomic particle that we haven't discovered yet. These aren't the familiar protons, neutrons, or electrons that make up you and me. These would be exotic particles that barely interact with anything except through gravity. Scientists have come up with a whole zoo of potential candidates. The most popular ones are called WIMPs, which stands for weakly interacting massive particles. These are hypothetical particles that are heavy, and as the name suggests, only interact through gravity and the weak nuclear force. So, where is all this dark matter hiding? Well, it's everywhere. It's in the vast empty spaces between galaxies, it's in massive halos surrounding galaxies, and yes, it's even passing through you right now. Billions of dark matter particles are likely streaming through your body every single second, but you don't feel a thing because they interact so weakly. This has led to a global race to try and detect these elusive particles. The search is happening on three main fronts. First, there are direct detection experiments. These are incredibly sensitive detectors built deep underground to shield them from cosmic rays and other background noise. The idea is that, very rarely, a dark matter particle might just happen to bump into the nucleus of an atom in the detector, creating a tiny flash of light or a vibration that can be measured. Experiments like the Large Underground Xenon Experiment, or Lux-Zeppelin, are essentially waiting in the dark, hoping for that 1 in a trillion collision. The second approach is indirect detection. If dark matter particles are their own antiparticles, they could collide and annihilate each other, producing a shower of more familiar particles, like gamma rays or neutrinos. So, telescopes like the Fermi Gamma Ray Space Telescope are scanning the skies, looking for an excess of these signals coming from areas where we expect dark matter to be concentrated, like the center of our galaxy. Finally, there's the brute force method, trying to create dark matter ourselves. At places like the Large Hadron Collider at CERN, physicists are smashing protons together at nearly the speed of light. The hope is that in the immense energy of these collisions, they might be able to create new, exotic particles, including dark matter particles. If they succeed, the dark matter particles would fly out of the detector without leaving a trace. Scientists would then look for events where energy and momentum appear to go missing, a telltale sign of an invisible particle escaping. So far, despite all these incredible efforts, we haven't found a definitive signal of a dark matter particle. We've found its gravitational shadow everywhere, but the particle itself remains a ghost. This has led some scientists to wonder if we're on the wrong track entirely. Maybe there isn't a new particle. Maybe our theory of gravity is incomplete. A few physicists are working on alternative theories, often called modified gravity, or MONT, which propose that gravity behaves differently on very large scales. These theories are interesting, but so far, they haven't been able to explain all the observations as well as the dark matter model can. The hunt for dark matter is one of the most exciting and challenging frontiers of science. Solving this enigma won't just tell us what 27% of the universe is made of. It could revolutionize our understanding of physics, from the smallest subatomic particles to the largest structures in the cosmos. It's a reminder that the universe is far more strange and wonderful than we can possibly imagine, and that there are still profound mysteries waiting to be uncovered, hiding in plain sight. What do you think dark matter is? A new particle? A flaw in our understanding of gravity? Let me know your thoughts in the comments below. Thanks for watching, and if you enjoyed this journey into the cosmic unknown, don't forget to like, subscribe, and hit that notification bell for more explorations of our amazing universe. See you next time.